calculating pH of strong acids. That's what we just kind of wrapped up on. We had an exam over that stuff. Okay. Now we're going to do the pH of weak acids. And if you look at all these situations, pretty much with all these pictures where it's the little fishies in the lake or bioreactors or brewing beer, what type of acids would you guess are involved in those processes? Jose, what would you guess? Because I guess what I'm saying is, statistically speaking, there's a lot more of which type of acid, strong or weak. There's a lot more strong, weak. Because there's only how many strong? 6. That means everything else is weak, everything. So, Audrey, how did we kind of recognize an acid? Just for our purposes, if I write down the chemical formula of an acid, how did you pretty much guess that it's an acid? What was their convention? What do you usually see? Yeah, you see an H out is the very first thing that they write, right? It could look, and then you add anything. You would guess it's an acid simply because you see an H written out front, okay? So if it's not one of the 6, it's got to be weak. So what we're going to spend some time on today, and the big goal is, hey, if you have 0.2 molar of this stuff, which is called acetic acid, vinegar, what's the pH? So since if it's weak, I guess this is where I'm coming from. Let's say you have 0.2 molar of that stuff. Then the hydrogen ion concentration is not equal to 0.2 molar because it's weak. So it can't be. So you got to figure this out. And once you figure it out, then you take the log of it and get the pH. But okay. Oh, I kind of already answered this, Kendall. How do you recognize a solution of a strong acid?
The strong acid? The H.
Yeah. But whether it's strong or weak, there's always an H out front. One of the 6, exactly. One of the 6. Oh, we should probably say what those 6 are so we don't mess this up. Cameron, name some strong acids for me. See how far you can get here. HCl. HCl. Use the periodic table. I'll give you 3 of them. HCl, HCl. Go down the halogens. HCl, H. No. Someone see where I'm pointing at? HBr and HI. There's your 3 right there from the periodic table. Okay, now you got to get the 3 that aren't in the periodic table. Kenneth?
H2SO4, HClO4, and HNO3.
Yeah. So I guess be careful with the homework, because if they do give you 0.1 molar of any of these 6, you know what the hydrogen ion concentration is. It's 0.1 molar. Take the negative log of it, and you're done. So if it's not one of these 6, how do we recognize a solution? It's not one of the 6, right? Not one of these. Okay. So for any weak acid, let's just call it HA. How can you write its acid ionization? They call it the dissociation reaction. About it, we could probably write HA goes to what plus what? Yes, H plus and A minus. Exactly. In general, you can write it every single time that way. In fact, no matter what the weak acid is, you can kind of make things easier just by writing this. So it's going to be the exact same format every time. How should we write the equilibrium constant? Or the acid ionization constant. They call it the Ka expression. That would be what over what? Andromeda, that would be what over what? Products over reactants, which would be A negative in brackets times H plus divided by HA. Because you notice I'm already lazy. I should be writing what subscript on everything up there, Steph? Aqueous, because we're always talking about water. Everything's dissolved in water. So we should be writing AQ on everything. But whatever. Okay. A larger, smaller, no effect. A blank acid ionization constant. A blank acid ionization constant means it's a stronger acid. Right? Because all these Kas are supposed to be written in this format. So that means a big Ka means that you've got a lot of reactant or product.
Reactant. Right. Yeah, reactant. Or would be product is small.
If Ka is huge, you've got a lot of, if you got a lot of reactant, look at that. You can be dividing by a huge number. So that ain't right. If Ka is huge, you've got a lot of product, right? If Ka is small, you hardly have any product. So if Ka is huge, you've got a lot of product. Well, that would mean that it's a stronger or even weaker. On what range of acid would it be here? If something is a stronger acid, would it generate more H plus in solution or less? If this acid is stronger than the other acid, well, the stronger acid should generate more H plus. So if you've got a lot of H plus, that means you've got a lot of product. So Ka should be bigger, right? That makes sense? There's always these backwards arrows. So all I'm saying is if Ka is big, if Ka is huge, this backwards arrow is really tiny, right? Because you've got a lot of product, hardly any reactant, okay? So a larger acid ionization constant means it's a stronger acid because of a blank degree of dissociation. Because of it's playing around with the terms here. What does dissociation mean? Breaking apart. That's what this reaction's doing. So if it happens to a larger degree, that's just saying, hey, it happens even more. Right? So if you have a really large acid ionization constant, means you've got a lot of product. Same way of saying that is because you have a really high degree of dissociation. It's just the same way of saying the same thing. They're just using this terminology that we just need to get used to. You have a very high degree of dissociation, right? Here's your dissociation. Look, it's breaking up to a very high degree. So yeah, you have a lot of H plus around, much more acidic. Table 16.1 lists a bunch of Kas for some weak acids. Notice nowhere in here do we see any of the 6. They all have an H out front by convention, so they're all acidic solutions. Alyssa, which one can I circle and say, hey, that's the strongest? Acetic acid is right here. Is that the strongest? Everybody agree? No, that means you're seeing a number that's even bigger than this. There is, you're right. What number is even bigger?
Oxalic.
Oh yeah, oxalic is 10 to the negative 2. Oh yeah, you see, those are both 10 to the negative 2. Which one's bigger?
Oxalic.
Oxalic, right, because think of this as 0.056. This guy is 0.016. This one is 0.013. So which one's biggest? Oxalic. Yeah, this is right. So there's my strongest. How about the weakest one? The weakest of the weakest in the table. Anybody see it?
HS negative.
HS negative. 10 to the negative 13.
What about HPO4 though?
Is there anything smaller than that? What did you say? HPO4 negative 2? Ooh, that's 10 to the negative 13 also.
No, that makes this smaller. It's 4.8.
So which one's smaller? 1.2 times 10 to the negative 13? Or 4.8? Now they're both 10 to the negative 13, so don't even look at that part. So what is 1.2 or 4.8 smaller? 1.2. Kenneth, you catch that? They're both 10 to the negative 13, so we don't look at it. Just compare 4.8 and 1.2. Make your life a lot easier. So the weakest would be HS minus. Write the dissociation reaction for the weakest acid in the table. All right, here's a good test question, upcoming quiz question. Go ahead and write the dissociation reaction and the Ka expression for the weakest acid. And we said the weakest acid was HS minus. And remember, all these dissociation reactions are like HA, in the form of HA going to H plus plus A minus. They all have to be written in that form. But they want the exact reaction. So you should have something going to two products. And then your Ka expression. Products over reactants. Kind of a little trick to doing this, Steph. What did you write as your reaction? HS minus yields H plus and S minus 2. Perfect. Right? Because she had to subtract a minus, right? She took away a plus, so add a minus onto that sulfide. And plus, maybe you recognize sulfide, right? S has a negative 2 on it. You could add the charges, negative 2 and a plus 1 is a negative 1, so that's why I have a negative 1 over there. It works. It checks. So Audrey, hopefully you got that. What did you write what would you write as the corresponding Ka expression? Yep. Perfect. There it is. Okay. So we still haven't really answered the question, how do you get the pH of this stuff? Right? So here it is. Calculating the equilibrium concentrations of weak acid solutions when given its Ka and the initial concentration. So I doubt if they're going to give you this. You probably have to look that up in the table. But the problem, I'm sure, will give you this. What do you think will be the units, Kendall, in this initial concentration? Probably what? Or hopefully what? If they give you initial concentration, the units will probably be big M. And if it's not, well, I hope they don't. That would be a lot of work, right? Because all these Kas, all these equilibrium constants depend on big M. But I'm sure they are. Like, look, here's 0.1. Okay, so I think we'll be okay. Formic acid is used to make ethyl formate, artificial rum sweetener. What's the pH of 0.1 molar solution of formic acid? And they give us Ka. So they want to know what is the pH. So how do I calculate pH again, Andrea? pH was what?
H plus
Negative. I gave you these negative later. So I gave you these equations, but I'm just driving at that saying, look, we got to somehow figure out what this is, and then we'll plug it in. So how are we going to find it? What we're going to do is we're going to write, we know what the Ka is. It's going to be a quadratic formula problem. Maybe, maybe not. Let's try it. We're going to have to plug in, write a reaction, write the reaction for the Ka, do ice, substitute everything in, get our X. I'll show you. We have HCl CHO2. All right, because this Ka corresponds to this reaction. So we have to write that reaction in the exact format they want. And the format was, remember, HA going to H plus plus A minus. So it has to have that acid on the reactant side. Whoop, not A minus. I guess, see how it really doesn't matter, even if you did write A minus? CHO2, because the math is going to be the same. But, okay, ice. And the initial row, we've got our 0.1 molar solution. So we'll put that in. Dashes, because there's nothing else there. The change row. Cameron, what will we likely, you think, put in the change row? Minus X. Then these guys are forming, so these might be plus X's, right? The stoichiometric coefficients are all ones, so just minus X for reactants, positive X for products. Bowdy, how do we get our answers again, our equilibrium concentrations?
You do like 0.1 minus.
Yeah, let's add them up. 0.1 minus X. X plus 0, X plus 0. So find that hydrogen ion concentration. There it is. It's right there. It's X. You just got to find out what X is. Take the negative log of it, and we'll have our answer. Okay. So odds are we'll probably set up what next, Anessa? Ka expression.
X over 0.1 minus.
Whoa, 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 we're going way too fast. Ka is 1.7 times 10 negative 4. Oh, let's just write the expression. Since this is our first time, let's not skip anything. And let's not skip anything. Our Ka is going to be what expression? What over what?
Plus concentration.
Yeah.
Times CHO2 negative concentration over HCHO2 concentration.
Yeah. Okay, so when you get used to this stuff, and you do a bunch of these, you know, you probably feel a lot safer to skip this, but that way now you just plug everything straight in. This is where Anessa was talking about before. She's going to plug in all these numbers, and the Ka is going to be 1.7 times 10 to the negative 4. Products over reactants, X times X all over 0.1 minus X. Okay. So right now, I don't think you're a very happy camper, right? But I'm going to tell you something that's going to hopefully make you a very happy camper. Because you're not a happy camper because you see quadratic formula on every single homework question. And Audrey's just going, oh my gosh. All right. I say that, how can I explain this the best way? The best way is kind of what was confusing you at the beginning, I think. If this is a, let's pick a different color here. If this is a big number, the bigger this is, the bigger that is, then X will be smaller or bigger. If this is getting to be bigger and bigger and bigger, X gets bigger and bigger and bigger, or smaller and smaller and smaller. Right? If my Ka keeps getting bigger and bigger and bigger, X's will be bigger, right? Because remember, all K's are products over reactants. So if K is really big, my X is going to be really big, right? And then just follow the logic here. If my X is really big, 0.1 minus X, I'm going to get something really appreciable, right? It's going to be a problem. But imagine it the other way. Ka, because K is really small. Because we're talking about weak acids in the first place. All our Kas should be really, really small, because they're supposed to be weak. And the weaker they are, even the smaller Ka is. So, and look at these guys, 10 to the negative 11. We're talking about a tenth of a billion in 10 to the negative 10. These things hardly even start, and they already quit, right? You hardly get any product on this stuff. So if you hardly get any product, these X's, when these Kas are really small, these X's are going to be really, really small. If I take 0.1 minus something really, really small, a tenth of a billionth, you essentially get 0.1 again, right? So what I can do is I can say, oh, if I take a number minus something really small, I essentially get that number. This should make you really happy. I'm going to do my squiggly lines, which means what? Approximately. I can't mess with the top, because a small number times a small number, you can't mess with it, right? That's going to be, but if I take 0.1 minus a small number, I essentially get 0.1. Now do you have to do the quadratic formula? No. Because x is, let's see, x is going to be a tenth of a billionth, right? A billionth is 10 to the negative 9. A tenth of it is 10 to the negative 10. So how would I write that? I have to write it 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I can write my 1. So I'm taking 0.1 minus this number. Now, yeah, you'll get something in your calculator, but it's going to be 0.1. I'm just guessing, because I'm saying, look at what my KAs are. So I'm just guessing, saying, hey, these are going to be really, really small numbers. So then I can just write this. And then how would I solve for, I end up having 1.7 times 10 negative 4 equals x squared over 0.1. Now how would you solve for your x here? Multiply by 0.1, then take square root. Do all that in one step. Don't be writing anything down. Multiply it by 0.1, take the square root. So you should get about, if you did this right on the calculator, you should get about 4.12 times 10 negative 3. Make sure you can get that.
What did you say she got?
4.12 times 10 to the negative 3. Jose, you got it? Okay. So you got it? Cameron, you get it? You don't even have your calculator. So bring a calculator class, dude. Okay, 4.12 times 10 to the negative 3. They want to know the pH of this. So what do I do? Put it in the log, exactly. Because pH is negative log of H, and H is my hydrogen ion concentration. So just take the log of that number that's in your calculator. Whoop. Push the wrong button. You get about 2.4 or so, right? Perfect. That's my answer. All right? Take the log of it. What if they asked for what's the POH? What would you do? Subtract from 14. Yeah, do it. Right? That's not no big deal. Okay. So doesn't this sound nice? Andre, it's better than the alternative. Okay. Now you don't have to do this trick. You can do the full quadratic formula, follow it through, and you will get the exact answer. It might be 2.398 or something, right? It's going to be really, really close to this. Or it's going to be 2.40001 or something. Okay? So it's good. The problem is there's a threshold where you're not going to get the right answer by doing this anymore. Right? That's where the trick comes. The trick comes looking at this table and recognizing, oh, which ones are going to give me really small x's? Okay? And the trick, I think, the threshold is that 10 to the negative 4. If you have KAs that are bigger than 10 to the negative 4, you don't want to see those on exams. You don't want to see those on quizzes because those x's are going to be big, and Smith is going to expect you to do a full quadratic formula. Okay, how do you know? Yeah, Good, Mia. How do you know? That means you have to know. You have to have a table, right? You have to know what the KAs are. But to do the problem in the first place, they have to tell you what the KA is, or you have to look it up in the table. So you know what the exponent's going to be. So let's think of things negatively. You do not want to see, you do not want to see which acids? Circle them. Circle the acids that you do not want to see. Circle them. Because if you do see these acids, no matter what they, bless you, no matter what concentrations they tell you, no matter what the problem is, you're going to do a full quadratic formula. Circle them. Okay. Mia, tell me one of the acids that, tell me one of the acids that you circled. We're circling for the ones that you don't want to see. Which ones did you circle?
I circled the
Acetic acid is 10 to the negative 5. That number is smaller. So that's a good one. You would like to see that one. That's why we're going over this. Which number is, what exponents are you looking for? 10 to the negative 3, 10 to the negative 2. Those are the ones you're looking for, right? Those are the ones you're looking for. That's why we're going through this, because it's confusing. So which ones let's pick on, Alyssa, which ones are we going to circle then? HSO4. Oh yeah, you don't want to see this one. You don't want, Mia, what else are we going to see? Phosphorus acid. Good. You don't want to see that one. Anyone else? All right, here's another one. Here's another one. Phosphoric. So that's about all of them, right? So those are the ones you don't want to see. Make sense? So try it. Find the pH of a 0.38 molar hydrogen cyanide solution. And I'm giving you what the Ka is. I mean, you could have looked it up in the table, but I just gave it to you. You want to open the window? Yeah. If it bothers me, I'm definitely opening this. Just close it if you get cold over there. Or Mia, maybe sit up front. Look at all the nice warm air up here. All this hot air is being blown around up here. All right, so hopefully you got an equation set up like this. You ended up with x squared over 0.38 is approximately 4.9 times 10 negative 10. You're on the right track if you're getting that far. Then we go through some work. You get the pH to be what? What did you get, Andromeda? 4.9? I hear like 3 4.9s. It's supposed to be a 9. Gosh. So I'll get something really close to 5, and I think you're doing it right. If you got it, go on to the next one. If not, let me help you out. Make sure you can get this.
The pH in and find H concentration H plus
Mm-hmm.
backwards.
Yes.
Okay.
Yeah. Got 4.9?
Yeah.
Good job. Oh, you guys got it.
Yes, sir.
Everyone's on EX3. You got 4.9 there, Cameron? Okay. Okay, you guys are all on EX3. Good. All right, let's flip it over then. There's always curveballs. This is definitely a curveball. Definitely a curveball. Does anybody have a game plan? Steph, what do you think?
Work backwards to get you the pH.
Yes.
H concentration.
Work backwards, she says. Get H from this. And how does that help you?
And then when you write the HA equals H plus A,
HA. Yeah.
you know your concentration of H.
Yeah.
So
Oh.
just subtract that.
So we know the concentration of H. We're getting close.
And then you know HA is at 0.52.
We know the HA is 0.52. What's A minus?
Same thing as H plus.
Same thing as H plus. All right. Now, if you can't see, because see how she's saying, Steph is saying, okay, now you've got that one. We know this guy. All right. This is the one that we're not sure, but Kendall says it's the exact same as H plus. If you don't see how or why, you could just finish the story. And finishing the story is just doing ice. Finishing the story is just doing ice. So you could say, whoa, what happened there? Right? They're saying that HA is 0.52. We do dashes. Minus X, X, X. And then they said that the concentration of HA is 0.52, so there is no minus X here. They're just saying, hey, these are your answers. This is your equilibrium. So I agree with Kendall, right? H plus and A minus are the exact same concentration. So once you get X, once you get that hydrogen ion concentration, you know what they are. So you can plug in what Ka would be. All right. So get what that X is, and then you'll just be squaring it, dividing it by 0.52, products over reactants. See what you get. So I got 1.58 times 10 to the negative 3 for the H plus. Hopefully you got that. You're going to have to put that in for x and square it, divide it by 0.52, and you'll have your answer.
I'll just look.
Get around 5 times 10 to the negative 6 is the final answer. About 4.8 times 10 to the negative 6. So if you got it, keep going. All right. So I ended up with about 4.8 times 10 to the negative 6 is the final answer for my Ka. With the time we have left, see if you can work through the rest of these.
Is this the equilibrium or the initial?
They're saying that, yeah, that's English is hard, isn't it? They're trying to say that's the initial.
Okay.
They're trying to say that you made this solution of HF, so that's supposed to be the initial. Yep.
Sure. Is this only one to work around full quadratic, or is this just the cutoff point?
10 to the negative 4 is the cutoff point.
Okay, so it's not the cutoff.
It's the one where you're not getting the best answers, but they're acceptable.
I got scared.
Okay, so concentration, so what do we do the ice differently? Right?
Well, it just means you need all those answers in the E row. You need all the answers right here.
Okay.
That's your concentrations. So you're going to have to,
So I can go straight to this, right?
yeah, you could if you want, if you can see it without writing the whole ice expression. Products over the reactants. Yep. It's just kind of, I don't know, I guess I'm always writing this, I'm always writing out that reaction. Because life just gets, in this class, it seems to get more and more complicated. They're going to throw something else at you. So even though you can see the expression to write, Ka equals products over reactants, I just end up writing like the entire ice table every time, because it's just going to, you're going to see what's coming up is going to get, it's kind of the same thing, but it's confusing. So it's good just to have good habits and write everything out. It doesn't take very long. You won't make silly mistakes. Did you guys get answers for number 4? Oh, let me write them down. What did you get for EX4 for HF? What did you get, Bodie? Just so I can put in these answers, see if everyone else gets them. Oh, you don't have them? Megan, you don't have them either? 0.01 for HF? No, I don't know if you guys did this. 0.01 is the answer to HF? No, H plus and F minus. Yes. You're doing this right if you got... Right, because they're both the same, right? They're both X. So your answers for H plus and F minus had better be the same. You should get 0.01 for them. So 0.15 minus 0.01 is 0.14. Okay, so those are the answers you should be getting for number 4. So it's right at the limit, 10 to the negative 4. It's the last guy that we can drop the x's on. I think there's one left. Anybody get an answer already for 5? 1.9 is the pH? Anybody else get 1.9? Okay, so around 1.9. Sounds like a lot of people are getting that. Right, see if you can get 1.9 for the last one. You get Megan?
And then he's like, put another one. I remember how he got the really expensive was like knowledge is better than knowledge is better than knowledge. Oh, you know why I know?
Got it, Jose?
Yeah.
Awesome. Alrighty. So have a good day, and if you have any questions, come on by.